Today we'll look at different connection methods available in Simcenter 3D. Mesh mating conditions are great for creating connections across solid bodies. However, they can't be made across different solid bodies and different component finite element models in an assembly finite element model. Stitching is a very powerful way to connect multiple sheet bodies with a congruent mesh. As with mesh mating conditions, this cannot be accomplished in an assembly finite element model. Glue solves all of these limitations and is a great way to connect shell or solid meshes, even across components in an assembly finite element model. (1D) connections are very powerful. Some of the commands have geometric associativity. They do not support selection recipes, which we will talk more about in just a moment. Simcenter 3D has automated some of the more popular complex connection workflows for welding and creating bolted connections. Selection recipes are a way to collect objects for meshing or applying loads. When used in combination with part templates, they can be used to automate building a finite element model. Universal connections are the next generation of automation for creating 1D connections. They can leverage selection recipes in their creation. Creating universal connections is a multi-step process involving first defining the connection and then realizing it to create the finite element model connection. Universal connections are supported in other solver environments like Abacus and ANSYS. Today we'll be focusing on its application in the Nastran solver environment. The bushing universal connection automates creating a C-bush with optional RBE2 spiders. The dialog has a few steps to define the connection. Defining the targets has several options depending on if the spiders are desired on the ends. Also, the target 1 specification determines what options are available for target 2. There are several options for specifying the coordinate system for the orientation of the bushing's physical properties. There are also options for specifying the type of coordinate system for the bushing's physical properties. Instead of specifying the physical properties in the mesh collector, it's done in the bushing definition dialog instead. And then the last step is to realize the universal connection by selecting the desired element type. Rigid universal connections are similar in how they're specified. However, the target matrix you can see here is a little different depending on the target 1 that you select and the target 2 options that are available. We can specify the coordinate system for the orientation, the degrees of freedom based on that coordinate system, and the element type as either RBE2 or RBE3. Let's take a look at how universal connections and selection recipes can be used in a demonstration. Here we have an assembly consisting of a board and pedestals. And what we'll do is we'll create an assembly finite element model. We'll begin by creating component finite element models, first of the board. We'll begin creating a mid-surface of the board. I'm going to use layers to manage visibility. I'd like to get an associative copy of the solid body of the board on layer 11. And we'll turn off our original layer where the component is, and we'll create our mid-surface. Now I don't want the mid-plane mid-surface. I actually want the face that's coplanar with the pedestal. So I'm going to swap my face pairs and go for side 1 face so that I get the bottom face there. Then we'll go ahead and bring in that mid-surface into our fem. So now, to stay consistent with our naming conventions, we'll make sure that we're going to create our mesh on layer 11. We'll go ahead and put a C-Quad 4 shell mesh on there with an element size of 0.2. And what you'll see is that we don't need to specify physical properties because we're going to inherit those from the CAD model where it was already specified. The material was specified as copper. As well, we don't need to specify thickness because we're inheriting that from our mid-surface. So here you can see we've already got thickness assigned. Alright, so that looks good for the board. Let's go ahead and create a component fem for the pedestals. Here we're not going to use any bodies at first in the fem, so we're going to make some modifications to the pedestal component in the idealized part first. So here we'll make our work layer 12, different from the board. We'll create our associative copy using the wave geometry linker. And make sure we turn off our original layer where the component is on layer 1. Alright, now we'd like to assign some face properties. So we want to make sure we select in the selection bar face so that we're selecting the face, and then right click on it to select properties, and we're going to give it a title of pedestal face, and this will be our pedestal face number 1. So we'll give it a value of 1. That will be our attribute that we want to assign to that face. Now we're also going to create some points that we'll use in the fem in just a moment. We're going to create 2 duplicate points at the same arc center on the top of that pedestal. It's going to be so that we can attach each point to each end of our 0 length C-bush. And just so we can illustrate that a little bit better, I'm going to create some more points. These will be offset from the center of the shorter pedestal. First one will be a 1/4 inch offset, second one will be a 1/2 inch offset above the center of the pedestal. So that will create another bushing universal connection there so you can see in a little better detail what the selections are. So let's go ahead and bring that solid body with those attributes in, along with the points. Make sure we select geometry options, points, to bring in the points into the finite element model. They won't come in by default. Then to maintain our layer conventions, we'll make sure we're creating our finite elements on work layer 12 in the fem. And then we'll go ahead and put a 0.2 C-tetra 10 mesh on the pedestals. Here again we're going to inherit the material properties. You can see their aluminum 6061 was inherited from the CAD model. Alright, now we're going to create some selection recipes that we'll use later in creating our connections. First one will be an attribute selection recipe. This will define our pedestal face for one of our connections. And here we'll use the attribute that we had defined earlier as our pedestal face with a value of 1. And we have to hit the tab button there after typing in the 1 to get it to input in the dialog, and then you can see that face selected. All right, next we'll create our assembly finite element model off of the bushing 2011. And we'll go ahead and map existing individually so that we can maintain the layers that we had defined in our component finite element models. We'll say list only associated models to make sure we're getting the right model, and we'll say use original for our layer option for the pedestal and the board. All right, so our work layer will be 11. We'll also show 12 so that we can see both the board and the pedestals. Now we could create a simple 1D connection node to node with a proximity spider where we only need to select the leg nodes and create an RBE2 connection between the top of the pedestal and the nodes on the board. So here I can select those nodes using the smart selector, related nodes to the polygon face at the top of the pedestal. So that's a fairly easy pick, but the nodes on the board are not as easy. I'd like to maintain that nice mapped shape to that mesh and only get the nodes that are within that pedestal. So to do that, I'm going to use layers, and I'm going to make the layer that has the pedestals visible only, so I can't select anything on it for my next pick. And we'll go ahead and just zoom in on that so we can see the outline of the pedestal a little bit better through. And we're going to use a circle select and make sure we're back to no method, so we're just getting nodes, and I'll drag a circle the size of the pedestal to just get the nodes on the board. So we can make this type of connection very quickly and easily. However, since it's a node-to-node connection, it will not survive a CAD change and a finite element model update. So while we were able to easily create this connection, it won't survive a CAD change or a finite element model update. So I'm going to go ahead and undo that connection. And we'll create it using a rigid universal connection that will survive a CAD change and a finite element model update. So how are we going to select those nodes on the board? Well, we'll do that with a selection recipe. We'll define a proximity selection recipe, which we'll call board nodes 2. So that'll be above our second pedestal. And we'll specify we're only going to select nodes in the board mesh. We're going to look for nodes, and it will be just a little over an inch above the polygon face of the top of that pedestal, because that pedestal is just an inch below the board. So I'm going to make it just a slightly larger search distance to find those nodes right above the pedestal. All right, now we'll create our rigid universal connection, and we'll start by specifying our targets. We'll use spider for target 1 and none for target 2. We'll use legs at the center of gravity and just select the legs. Our first one will be a selection recipe, which will be our board nodes. You can see we've selected one item, and then the second will be our polygon face. So there you can see it's got all those nodes that it's making a rigid connection between, putting the center at the center of gravity of those nodes. Now that connection is not realized yet. We need to specify what elements we want to create, and now it's up to date and it's been fully realized. There you can see the universal connection and also the 1D elements that it's created. All right, and that will survive a CAD change and a finite element model update. All right, next, to be able to collect the nodes above the next pedestal, we'll call this one board nodes 3. And we can put in spaces if we want or not in the names there. Again, we'll select the board mesh and the face of the pedestal with the same tolerance. That's also an inch away from the board, to get those nodes above that pedestal. But this time we're not going to create a rigid connection. We're going to use those points to create a bushing universal connection. And we'll specify target 1 as being a spider, because we want to create a rigid spider on both ends. Target 1 and target 2 will have a spider. But our center selection, we won't use legs of COG. We're going to use those points that we created to manually select the center, and then the legs as well. Then we'll select the point as the center for our target 2, the other point, and then the board node selection recipe for our leg selection for target 2. All right, so there you can see our bushing element between the two rigid spiders, all created in one shot and fully associative to the geometry. We'll go ahead and realize that there's no other options other than cbush and RBE2 when in the Nastran solver language for the cbush, for the bushing universal connection. Now I did forget to specify an axis type. We can go ahead and tell it we want to use the absolute, and we can also specify our physical properties, which are sticky from the last time that you used the dialog, but you can put those in whatever units you're comfortable. All right, so you can see there's an update pending because I changed the axis, and we'll just go ahead and hit the update button there, and we've got our update. Now, lastly, we'd like to create a zero-length C-bush with RBE2 spiders for our tallest pedestal here that's coplanar with the board. We'll first create a selection recipe that will be board nodes 1 that will have a tolerance above the polygon face of 1/10 of an inch. But until I hit the tab key, it's still thinking it's 1.01. So I'll go ahead and hit the tab button there and the tolerance, and we get the nodes that we're after for board nodes 1 selection recipe. Then we can use that in our next bushing universal connection. We'll do this the same way, spider, spider, manual, manual, using points, but here we have two duplicate points that are right on top of each other, and we need to use the first point for the first one. So I'll use the query selection, quick pick dialog, to select the first one, and then we'll use the polygon face for the leg selection for the first target. Then we'll use quick pick to select the second point for our target 2, and the leg selection will be our selection recipe that we just created, board nodes 1. All right, axis type will be absolute. Keep the stiffness the same, and it creates the universal connection, but you can see it's not realized yet until we specify what elements we want to use. All right, so let's go ahead and test out our solution. Make sure that, that this will run. First, we need to make sure we don't have any conflicts between our node and element numberings and our component FEMs, which we do. We'll go ahead and resolve them using the assembly label manager. Then we'll create a new simulation file where we'll create a linear static solution. We'll maintain our original layer placements there for our components and our linear static solution. And here we'll create a fixed translation constraint on one face of the pedestal component and a G-load. And solve. All right, here I'm going to pause the movie. This one takes maybe 7 or 8 seconds to run. Here you can see 8 seconds in the solution monitor. And let's take a look at our results. We'll just look at displacements to make sure that it ran. And that looks good. You can see the stiffness of the C bush there. and the board deflecting as a result of the G-load. All right, so now we'll go ahead and test the updatability and robustness of those connections by making a CAD change. We'll go back to our assembly and make the pedestals our work part, and then we'll go ahead and move some of the pedestals around. And we'll use the synchronous move face to do that. Here we need to specify a pivot point. Now let's go ahead and drag it over to the other side. And we'll move all of the pedestals around. This one might be better to move in the Y direction. And then we'll move the last one as well in the Y direction. All right, so that looks like a good CAD change. Let's see how our connections survive this update. So here you can see there's a number of universal connections that need to update in the assembly finite element model. But first we'll go ahead and check and update our component finite element models. So here you can see everything has updated properly, and we can go ahead and update our assembly finite element model as well to get those universal connections up to date. And then we'll run the label manager to resolve any conflicts with the nodes and elements, and we're ready to run our updated solution. But just so that we can see a side-by-side comparison, I'll go ahead and clone the original solution, and we'll give it another name before we go ahead and solve. Again, I'll pause the movie another 7 or 8 seconds to solve, and we can take a look at our results side by side with our original and our change. And here we'll look at the displacement from the original on the left, the displacement results from the updated model on the right, and we'll synchronize the views, and we can go ahead and animate both of them as well. And that concludes the demonstration.